The problem says the buckets on a conveyor move at a speed of 15 feet per second. Each bucket carries a block, which falls out when the angle is 120 degrees. Find the distance S where the block lands on the conveyor, ignoring the size of the block. So essentially you have a chain and sprocket mechanism that is rotating, and attached to the chain, you have a bucket carrying block at 120 degrees. The block discharges from the bucket, and we want to see at what distance S it'll fall on the conveyor. So this is a mechanical system. We know dynamics is, or vector dynamics is a mechanical engineering course. So I picked a problem that has a mechanical engineering application behind it. We'll be utilizing some concepts in this problem. The first thing we want to do is we want to define our reference frame. Okay, so our reference frame essentially is, it's going to be the point where we're going to be measuring our kinematic parameters, in this case, position, velocity, and acceleration. So I drew it at the center of the sprocket. At the same time, I'll let the discharge point be A, and the point where the block lands B. Okay. So once again, A and B. We'll start by solving for the X and Y coordinates for A and B, because as you know, we're going to end up using projectile motion. How do we know we're using projectile motion? The path of the particle, parabolic. This is a rectangular coordinate problem where the acceleration in the Y is equal to negative G. Acceleration in the X is 0. Okay. So once again, we draw the sprocket separately so we could understand the angles. So point A is here, let's say. You have the origin. The radius is 1 feet per the image or figure. You have okay. So we got that so far. Essentially, we know that the angle from here to here is going to be 180 degrees. 180 minus 120 is 60, so that's 60 here. Essentially, I'll draw a line here. We'll see that this is a right angle. Okay, so this is 30. We'll draw the x-axis. One critical concept that this problem pushes students to recognize is that the velocity at the discharge is tangent to the path. The path is circular in nature. So at every instant, it has to be perpendicular to the path, or tangent to the path. It has to be tangent to the path. Okay. So therefore, it's tangent to the path. It makes a 90-degree angle with the radius, the radial axis. Looking at this, 60 degrees. With a horizontal axis, it'll be 30 degrees. We'll let this be equal to VA. We need to find the XA coordinate and then the YA coordinate measured with respect to our reference frame. Okay. So XA, it'll be 1 sine 30. YA, it'll be 1 cosine 30. 0.5 feet, 0.866 feet. So that's what we got so far. We got the coordinates of A. Okay, the coordinates of B, XB is going to be S variable. YB is going to be measured with respect to our reference frame. It'll be -3 feet. So we got our coordinates. And we'll use these coordinates for our kinematic equations. Okay, so we'll start with the horizontal motion or the x direction motion. So x direction motion and projectile motion. Remember projectile motion is a special application of rectangular coordinates where ax is equal to 0 feet per second squared, which means that the velocity in the x direction at any instant of the projectile motion is constant. Okay, so essentially we'll solve for the x component at a of the velocity. The discharge velocity is 15 feet per second, so essentially it's 15 cosine 30. How do I know? We use the reference angle here that we calculated. So 15 cosine 30. Essentially we have a velocity of 13 feet per second. Okay, so that velocity in the x is constant, so we could just label it as Vx because it's not going to change regardless of point. So now the only kinematic equation that we could essentially use in the x direction, based on the fact that the acceleration is 0, is the following. So essentially the velocity in the x direction is equal to the instantaneous change in the x direction with respect to time. We separate variables where we have dx is equal to Vx dt. We have XA and XB as your boundary conditions, dx, and then you have 0 to t, dx dt. Your overall kinematic equation is XB is equal to Vxt plus XA, okay? So based off of this, we said XB is equal to S. We said Vx is equal to 13 times t. We said XA is equal to half. So essentially, S is a function of time so far. We don't know S or T, but this is an equation that we'll use to solve for our unknown, which is S, okay? So since we didn't get the answer just by doing the X direction, we have to analyze the Y direction motion too. Okay, so essentially, we know that acceleration in Y is equal to dvy dt. Okay, so acceleration is the instantaneous change of velocity with respect to time. In many cases, we don't do the derivation for the equation, but I just want to show you if you want to take if you want to see where things come from and you request it during tutoring sessions, I'm more than happy to show you the extra detail. I'm more than capable in doing so. But then again, these are standard equations, so in many cases, it's not necessary. So essentially here, we'll plug in our parameters that we defined from the beginning, YB and then YA, of course. So YB, we said it was -3. So 1/2 the acceleration in the Y is minus G. So in feet, essentially it's 32.2 feet per second squared. In the negative direction, because the gravity goes down. And then VAY essentially is VAY will need to compute. So VAY is equal to minus 15 sine 30. How do I know that? We look at the picture, we look at the direction of velocity. The velocity goes this way, has a negative y component, take the sine 30 of VA, and essentially that gives you the y component. So minus 15 sine 30. That gives us minus 7.5 feet per second. So minus 7.5 t. plus, what is our YA? Our YA essentially is 0.866. So essentially we have, essentially move the 3 to the right side, and essentially we have the following. We're gonna have 0 equal to minus 16.1 t squared minus 7.5 t plus 3.866. We plug it in the quadratic formula, my bad. So t is equal to minus b plus minus b squared 4ac, and then 2a. Essentially what we're trying to get is we're trying to get the roots to solve for time. So we get T1 negative, and then we get 0.310 positive. We pick the positive root. So that essentially tells us the time for the box to go from A to B. So we'll use that same time in this equation to solve for S. So S is 13t plus half. S is equal to 13.310 plus half. We get 4.53 feet. And that essentially summarizes our problem. The box is gonna essentially fall at 4.53 feet from the point of release, or essentially it'll be from the point of reference, okay, from our reference point. So now you see why I picked my reference at the origin here, so that when we solve for S, we solve for the parameter that yeah, essentially when we solve for S, we're solving it with respect to the desired origin that the problem is showing, okay? Just to keep it nice and simple. And then once again, I picked the problem that has a mechanical engineering application, a sprocket chain with buckets attached. Essentially, the bucket is going to reach a point where the box is going to slide, and it's going to get thrown off, and it's going to follow a certain curvature. We use XY coordinates, which is rectangular coordinates, and we use the special application within rectangular coordinates in the case where we have projectile motion. The projectile motion acceleration is 0 in the x direction, acceleration in the y is negative gravity. And then we derive our kinematic equations based off those two assumptions, and we solve for our problem, okay? I did go a little bit fast in this type of example. During tutoring, I asked for feedback at what the adequate speed is, and we do stops to make sure that you guys understand the steps. And if there's an explanation that is necessary for the specific step, I stop, I explain, and we address the questions live. The geometry, the trigonometry, sign conventions, why I picked the origin here, my notation, my derivation, the units that I'm using, sign conventions, all that good stuff. So I try to cover all bases. I try to be as neat as possible, and I try to ask for feedback throughout the tutoring session. That's usually the goal.